So if you remember last time we talked about what we talked about last class, anyone remembers?
Yes, about core, peer-to-peer and core.
So we talked about core and we talked about distributed hash tables, right? So basically, we were talking about the key value storage and how we can do this key value storage how we can store that and how we can do the lookup very fast, because we were concentrating on, especially like last week, we were concentrating on peer-to-peer networks. And we're saying, of course, there are millions of nodes connected to each other in a peer-to-peer fashion. How we can basically find the data that we are looking in the fastest possible. And also we talked about the challenges that we are having, like that churn that we have in the network, all those basically dynamicity in the network, joining new node, joining node leaving, failing. So how we can deal with that. So today we're going to talk about scaling out key value storage. We're going to talk about Dynamo, Amazon Dynamo. So we talk about that key value storage in a peer-to-peer way. Now we want to see how we can scale it, okay, for a distributed system, not just for a peer-to-peer network. So talking about scaling out, okay, we can have two types of basically scalability. When we're talking about scalability, we can have vertical scaling and horizontal scaling. Anyone can say the difference, or what does it mean, vertical scaling? Or horizontal scaling? Or just describing the picture that you're seeing, because it has the meaning, right, somehow.
Vertical scaling would mean that you want to add more resources to a single computer, right? Computer power, storage capabilities in a single computer, right? Computing power. Horizontal scaling would be like you want to add additional computers that probably are not as potent, but together they are like, yeah, they can work faster if they work together, right?
Mm-hmm. Yeah, that's true. Nice explanation, Luis. Vertical scaling, as we said, it means adding more resources to the computer or the server that you're having, putting more CPU, hardware, RAM. Okay, so that's how you're basically scaling. You're requiring more resources, so you are scaling your server by adding more resources, or your computer, whatever you consider it. Server, let's talk about server. So that's, you have one and you're just scaling up because you have more data coming, maybe more users. So you start putting more RAMs, higher, like stronger CPU, more hard disk in order to increase or scale the resources of the computer or the server that you have. But the horizontal scaling is like adding more nodes to the network that you have, or like replicating data and adding more nodes into the system that you're having. So talking about the vertical scaling, basically you could have just a server. Even you could do the replication of the server still. Okay, so you have one server, that's your main server, then you can replicate it. Like in a like traditional way, that was the way that a lot of systems are working, right? Before, let's say, all this distributed computing things. So you have a server, so users are connecting to get your business grow. I don't know, your server needs to handle more people, or higher, I don't know, the bigger database, so you start adding resources. But the horizontal scaling, adding more nodes to the network. But the thing is, when we're talking about the availability is important, then that's the horizontal scaling is the way to go. It's not, basically, you cannot deal, I mean, you cannot do that with vertical scaling, because in vertical scaling, you still have the single point of failure. But that's why you wanna, when you wanna have an available system, like most of the time available, so you wanna add more nodes, or you wanna basically scale your system horizontally. So that's what we're going to talk about, horizontal scaling. It's challenging, of course, because no matter how basically, what is the rate of availability of the system, okay? If you consider how like even the system or servers this much available, okay, like 99.99999% of the time available, but when you have a large number of machines, so you have a big number of basically failures. Your data centers or your system, your distributed system will experience big number of failures because I mean this is the, let's say, equation. You wanna, if your P is your probability of machine fails in a given period, and then N is the number of machines, so you can calculate the probability using this. So basic probability things. So you know, so considering this, you might, I mean, a lot of people think like servers or like computers are now very, very reliable. Okay, they don't really fail that much. So this is a very good reliability. It's not a really small numbers. Like this much availability for a system, it's really big number. That's good. But when you're talking about tens of thousands of hundreds of thousands of nodes or computer, the failure will become a big numbers. Like for this 50K, you can have 16% of failure in your distributed system. If you are using 100K machines, you can face like 30% failure, okay? So it's a challenging things, okay? So that's the whole idea, to make sure.
When you say a failure, you mean it can be one machine, right? Not a full cluster.
No, just one. So maybe,
Okay.
so what it means, like for 30% of the time using 100K machines, in 30% of the time, you have a failure in your network. Not all the network, like there are failure of, there are some servers that are failing. So the main challenge is coping with the constant failure, because you're talking about horizontal scaling, adding more nodes. So the main basically issue is dealing with this failure. So today we're going to talk about techniques for partitioning data. And a big part of it is the same thing that we discussed last time, okay, about consistent hashing. And then we're going to talk about Amazon Dynamo key value storage. So when we arrive here, I'm going to basically pause and ask the basic stage to the students to talk about that. Then I cover if anything was missing. So you have a key value pairs to be partitioned across nodes based on the ID. So you remember what we were talking the last class about distributed hash tables. We had a key value pairs, and we were using basically hash table, distributed hash tables to store that. So talk about this basically task. Okay, the first problem is data placement. You want to know on which nodes or nodes you want to place each key value pairs. And you need to maintain mapping from data objects to nodes, and you want to make sure that you are evenly distributing data, or you are evenly distributing the load across the networks. So this is what we discussed last time. The second part of the problem is partition management. That's one of the issues, because you have the failure in the network. So at some point, the network can be partitioned to two different parts or more different parts. So it's important to deal with that partitioning, network partitioning, and you need to basically discuss or consider how to recover from node failure. And another issue is like that high rate of churn that we were talking in P2P networks. Of course, that's not the case in distributed system. Okay, please don't confuse it. In P2P networks, peer-to-peer network, we have high churn. A lot of join, a lot of leave, a lot of failure, because we're talking about normal, unreliable nodes. Now here we're talking about distributed systems, servers, data centers with hundreds, thousands of servers. They are of course more reliable, but it's still, you at some point you want to scale your systems. If your business is successful, okay, like Amazon in like last few months, you want to scale the system, right? So when your business is successful, you want to add more nodes, right? And scale the system. And of course, maybe you want to, some of the nodes going to fail and they leave the networks. So you want to deal with all that issues. Also, another issue can be heterogeneous nodes. not all the servers again, or in all the part of basically physical location can have same type of characteristics, so they can be heterogeneous nodes. So you may deal with that problem using a centralized manner by clustering the basically servers in a centralized fashion, or sorry, using this decentralized way, like by talking, let's say, the same thing that we discussed, deterministic hashing and algorithms. So we talked about this modular hashing last time. I'm going to mention it a little bit more here. The same thing, just to remind and what is the issue here. So consider problem of the data partitions. You remember we were talking about CAP theorem. Anyone remember?
Consistency, availability,
And P?
Persistence? Partition?
No. Yeah, partition tolerance, right? So that was the CAP theorem, consistency, availability, and partition tolerance. And if you remember that time we discussed partition tolerance should be there, right? Because talking about this failure that we're discussing here, network at some point going to get partitioned. So partition is there. Now you have to deal with it. You have to a little bit maybe sacrifice availability or consistency, because you cannot, let's say you cannot say I'm gonna sacrifice and partition tolerance. It's there already. So we discussed about this modular hashing, okay, that you basically hash the, let's say, key, you put it in a distributed hash table, and then you can look it up fast, whatever we discussed last time. But let's say what happens if server fails, okay, or joins? How we can deal with, I mean, if we consider this is what we're using, okay, we place X or the data, okay, object ID X on a server with using these equations. So what happens if a server fails? Okay, let's say this is the object serial numbers. We have 5, 7, 10, and so on, and we have these 5 servers in the network from 0 to 4. So using this equation that we just discussed, the same thing that we were talking about last time. Okay, don't get confused by the equation. You do the basically you distribute that basically nodes in that distributed hash tables that we were talking about based on their IDs. So if this is the object's real numbers, and this we have 5 servers, and you put that in this equation to see which you want to put this object in which server. The same thing with distributed hash table that we were talking. So this is the first equations, right? So, but this is the placement based on the equations. So if you add one more machines now, if you add one more machine, now this mod 4, it becomes mod 5. This is the number of the servers that you are having. So now all these basically objects, they need to shift to different servers. You can see how many shifts do we have there. Now we have to basically, you remember that was the thing, right? We were talking if you added new nodes when we were talking last week about distributed hash table. If you add new one, then you need to move this data from just like this one to this one, because now this is the one that holds those certain IDs. So you see a lot of basically changes should happen here, and all entries get remapped to new nodes. So we need to move objects over the network, because this is now following that equation. This is a new placement. So that's an issue. If you just follow these methods, that's an issue. We already talked about how we can deal with that. I mentioned it maybe really briefly last time, talking about virtual nodes. So this is the whole idea of consistent hashing that we were talking. You assign n token to random points on a mod 2 to the power of k circle like this. Hash key size is k. So you hash objects to random circle positions, put object in closest clockwise bucket. Right? You remember what we were talking. Is there anyone doesn't remember? This is the same thing that we discussed last time, consistent hashing. So your successor key is referring to basically this is you remember, and you were saying you have the certain number of successors pointer link, right? If this fails, so you know the next successor is which one. So desired feature for this consistent hashing is the balance of the basically objects. You want to distribute the load. You want to have load balancing in the systems, right? You want all the nodes have certain amount of load on themselves, not most of the loads goes to one node and the other nodes be basically underutilized. And also you want to addition and removal of the tokens to be smooth. You want to minimize object movement for other buckets because you don't want this case happen here. When you add new modes, so now you have to start shifting all the data all over your basically distributed system. So these are the basically desired features. So consider this, you have like n nodes here, okay? Each node owns 1 to the n of the ID space in the expectations. Okay, so we have like 4 nodes, each node own 1/4 of the IDs. So if a node fails, its successor takes over the buckets. You remember that idea when this was basically failing. Now all this should go, all this basically bucket or all these IDs that are falling here, it should go move to this one. So we want, you remember we talked about the smoothness goal. We want to have basically localized shift. We don't want to shift a lot of data all over, okay? So we want to avoid this type of situations that if a node fails, a lot of load goes to another one and we need to shift a lot of data. So because this type of situation, it offsets the load balancing requirement that we have. So the idea that what I mentioned last time was adding more virtual nodes. So each, you're not adding, but it's like considering virtual nodes, because at the end it's like imaginary circle. Not that their nodes are really connected here to here to here. They're like, it's imaginary circle with the imaginary point on that. So you want to have, you want to consider virtual nodes. So each physical node implements V virtual nodes, okay? Each physical nodes maintain V bigger than 1 token IDs, of course. Each token ID corresponds to a virtual node. Each physical node can have a different V based on the strength of the node, okay? If you have a certain servers that are stronger than others, you can assign more virtual nodes. For example, this is my strongest server. I want to consider like 10 virtual nodes compared to a weaker server, let's say 5 virtual nodes. So let me explain it here, which make it much more simpler. Imagine these are the nodes that I have in my virtual ring, okay, connected to each other, but they are not necessarily they are physical nodes. They are virtual nodes. For example, this and this, they are the same physical server, because the V is 2 here. So each server occupying 2 virtual nodes. So basically what it means here, I have actually 3 physical servers, each one considering to have like 2 virtual nodes. Okay, so, all right, okay, I put here 4 physical nodes, but this, we have 4 physical nodes, and this is like same physical node, but 2 different virtual, 1 physical node having 2 virtual nodes. Are you lost? If you're not lost, there is something wrong because you're supposed to be lost by now. But the whole idea again, this is imaginary links, okay? Not that this server is physically connected to this server or this is connected physically to this server. We consider this set of IDs, if you remember, that they were discussing. This is the, like, they consider, I don't know, thousands of points, okay? And then we assign each physical server to certain IDs. That in that 1,000 imaginary ID, we assign them that IDs. But now here I say, don't just assign physical nodes to that ID. Assign like each physical node has 3 ID. Okay, so assign 3 random ID in your imaginary circle to this physical node. So imagine, for example, here, this and this are one physical node. So if this physical node fails, this node and this node is going to disappear because of one physical node. So that's the point here. So you can see, like, when this physical node is basically failed, you don't have to basically move a lot of data over, because now you have a better load balancing. And maybe even this is not very well describing it, but if you're imagining big numbers, a lot of physical nodes, okay, and a lot of basically virtual nodes, like imagine like you're assigning, I don't know, like whatever number, like 20 virtual nodes for each physical node, it will be distributed randomly. So this physical node will be this one, this one, this one, here, this one. So when one fails, there would be a very few data that needs to shift to the next basically physical nodes. So you're basically balancing the load using this manner. So especially with the larger V, okay, the virtual nodes, you can have a better load balancing. So let's talk about the Amazon Dynamo Key, because before I pass it to this, I want to say a little bit background, because when I see the slide, it's not there. So we already talked about distributed hash tables, and we discussed those in the context of peer-to-peer systems, wide area peer-to-peer systems, or basically individual nodes at the internet age, what we are using for so many things that we discussed: file sharing, cryptocurrencies, right? A lot of things. So the central challenge there was a low latency key lookup with high availability. So we trade off consistency for availability and latency. So for Dynamo, okay, we want to have this. We want to use the consistent hashing to make keys basically to do the same, to map keys to the nodes. We use this consistent hashing. We use vector clocks for conflict resolutions. We use gossip for node membership. These are all going to be described hopefully by the groups. If something missed, I cover it. And we want to do the replication at successors for availability and the failure. That's what we did also in the peer-to-peer system that we were discussing. That you don't want to just one node hold this particular key value. You want that to be replicated in different nodes. So if one fails, so you have another basically copy of it. So this is a little bit old data in 2007, because the paper is coming from 2007. The paper proposed, Dynamo paper was coming out in 2007 in an ASIM conference. But by then, Amazon workload was tens of thousands of servers, globally distributed data centers. So in the peak load, they have tens of millions of customers purchasing books, maybe mainly by those times. So they had it like tiered service-oriented architecture, a stateless web page rendering servers, a stateless aggregator servers, a stateless data stores. So what I'm saying here is just more like the context. You know the context of the papers, where the papers coming from, at what time, what was the situation there. So how does Amazon use Dynamo? It was used in shopping cart, session info, having the product list. And now I think there are more use cases for DynamoDB. I mean, it's getting much more popular now than in 2007. So the requirement for Dynamo is high availability rights, despite the failure. And why do you think is that? So the requirement is high available rights despite failures. You want to basically have high available rights. You want to basically your users be available always to do the right tasks. Because you want them to always keep adding to their cart, right? That's the worst thing that can happen for Amazon, is like when I'm trying to add a new product that I'm trying to buy into my shopping cart, I fail. That's the worst thing that happened, right? That's will directly affect their income. So you don't want that to happen. So you want your right will always be available. I mean, we are talking about the failure here, okay? So there are certain failures, partitioning, but you don't want all those affect your rights. So you want the customers always be able to add product to your shopping cart. So despite disk failing, network routes, flattening data centers destroyed by tornado, you want to have that right availability. So, and you want to always respond quickly, even during failures. Of course, you do the replications. And you will have low request response latency, like focus on 99.9% service level agreements. So you want to have it like incrementally scalable. Like imagine the growth that Amazon had. Of course, you want that insane scalability. So, and also you want adding a new nodes to be seamless, right? Without basically adding a lot of work, how to say, overloading the system by adding new data centers. So, and also you want to have comprehensive conflict resolution, because we're going to talk about it, because you want to consider high available rights. At certain points, a lot of points, the conflict is going to happen, okay? So you want to have a comprehensible conflict resolutions. So the question is, design question is, how is data placed and replicated in Amazon Dynamo? How are requests routed and handled in replicated systems? And how to cope with temporary and permanent node failure. So these are basically design questions that Amazon Dynamo or Dynamo is trying to answer. So I stopped here. So I passed the basically stage to the students, but maybe we can, if you want to have like 5 minutes break, so we don't stop in the middle of their presentations. Or if there is any questions. No? So remember the context. Okay, we already know the virtual clocks. Okay, but not virtual clocks. Vector clocks. We already know vector clocks. We already talked about distributed hash tables, short with the lookup service. So now we're going to talk about Dynamo. I mean, because it's using all those, so remember those. If you forgot, go quickly do the review on the slides before we start with the next. So let's come back 7:25, okay, with the student presentations.
Okay. Okay, so we're going to start talking about the Amazon solution for highly available key value store. In the end, Amazon developed nothing new, but the important thing is how they use all existing techniques and combine them in order to have this solution for their storing. So can we go to next slide, please? So what is Dynamo? Dynamo is the system that Amazon uses for highly decentralized, loosely coupled, and service-oriented architecture, which consists of hundreds of services implemented on top of an infrastructure of tens of thousands servers or more, and more network components, of course, located in many data centers around the world. So in this environment, even the slightest outage has significant financial consequences and of course impacts customer trust. So there is a need for storage techniques that are always available. For example, customers should be able to view and add items to their shopping cart, which is the best example in terms of Dynamo. Even if digs are failing, network routes are flapping, as we already saw in the presentation, or data centers are being destroyed by tornadoes. So the service responsible for managing shopping carts requires that it can always write to and read from its data store, and that its data need to be available across multiple data centers. So we can go to the next slide.
Okay, so as Hector mentioned, Amazon invented nothing new. The great thing or the great achievement, it was put everything together from the existing knowledge in the area. And we will see on this presentation about the scalability, availability, and how they managed to control all this process on the shopping cart, and with the session IDs to give the customer the best experience, because that of course represents an competitive advantage for the business. And at that time, it helped a lot Amazon to become the great company that we know they are by today. And there are on screen some of the subjects that we will cover in the next slides. And also we will see why they only care about write, and keep writing information in the database, and how they will handle how to read all that after. So the assumptions and requirements for Dynamo are the query model, which means they just need the get and the put operation, and to have that available, as we already mentioned. And we have some properties on the screen. And from those, the consistency is the one that they're going to care less. And similar to Baju, that will become with the time. They will look for consistency in the time. But what they care more is the availability for customers, and the efficiency, as we mentioned, that's because of the customer experience. They best all the business in that you should prefer shopping with them, because on how smooth it is adding items to the cart or searching items. And also please remember that all these Dynamo implementations happens under some environments which are totally internal in Amazon. So there are no hostile environments. They are not expecting any kind of security issues, hacking, or something related, because all the different considerations that they have, all given for the physical place where they are having their storage and their applications running.
Okay, how is the architecture of the Amazon service? There should be a way to guarantee that the application can deliver its functionality in abundant time. And for this, Dynamo uses the service level agreement, or SLA, which is a negotiated contract where a client and a service agree on several system-related characteristics. For example, one SLA, one common SLA in this kind of systems, of distributed systems, is the expected service latency. So an example of a simple SLA is a service guaranteeing that it will provide a response within 300 milliseconds for a percentage of its requests. So that's a common SLA. In the architecture of Dynamo, a page request to one of these sites typically requires a rendering engine to construct its response by sending requests to over or more than 150 services. So in this figure, we have an abstract view of this architecture. The dynamic web content is generated by page rendering components, which in turn query many other services. So a service can use different data stores to manage its state, and these data stores are stateless, as well as the aggregators, which are used by other services to produce a composite response. Can we go to the next slide, please? So what are the design considerations? In the end, Dynamo it's designed to be eventually consistent data store. So as we have seen in other sessions, in previous sessions, rather than dealing with the uncertainty of the correctness of an answer, the data is made unavailable until it is absolutely certain that it is correct. So in systems like this, which are prone to server and network failures, the availability can be increased by using replication techniques to propagate the replicas in the background and concurrently. So in this case, Dynamo targets the design space of an always writable data store. How this is done, let's say for a number of Amazon services, rejecting the customer updates could result in poor customer experience. For instance, the shopping cart service must allow the customers to add and remove items from their shopping cart, even if the network has failures. So this requirement forces Amazon to push the complexity of conflict resolution to the reads in order to ensure that rights are never rejected. So where is this process of conflict resolution performed? This can be done either by the data store or the application. And we have more design considerations like the incremental scalability, which is one of the key design considerations of Dynamo. The symmetry, which stands for no distinguish responsibilities for the nodes. Decentralization, which the design should be or should favor decentralized peer-to-peer techniques, and of course heterogeneity. The work distribution must be proportional to the capabilities of the individual servers. So can we go to next slide?
Okay, so for the other design principles, which the first one means that even if the network is suffering from any partition, the show must go on, so the user should be able to keep performing the get and the same put operation that we mentioned already. And that's something that differentiates Amazon from the competition, because Amazon standard is always almost at the 100% percentile of the good performance for their customers. And maybe some other companies work with 80%, 90%, but Amazon works at 99.99999, just to give the best experience, even on holiday or on high demand dates for the different countries where it is located. And as we mentioned, same as Bayou, it will get at some point to work and read all this information. So it is a zero hop because every node handles enough information to find the key that the client is looking for. So in that way, it will reduce the performance or the latency to come back with any answer for that request. Even if there is some 300 milliseconds time or more before sending the response, Amazon will drop that request and start a new one on a different node. So this is some of the things that we already mentioned. That as we saw, these are the most basic operations that we will perform in here. And the target are applications with less than 5 megabytes or around 1 megabyte of memory sharing between all the application nodes and client. And also all the data that is traveling in the system works with an MD5 hash.
So how is the system architecture? As we mentioned at the beginning, Dynamo advanced the state of the art by combining a lot of current available techniques. So in this table, you can see which is the problem being solved, the technique that solved this problem, the advantages. For sake of time, we will skip this, but we will describe more in detail in coming slides all of these techniques. So we can, okay. The first one, which is the partitioning and replication. So one key design requirement is that it must scale incrementally. So a mechanism to dynamically partition the data over the nodes available in the system is required. For this, Dynamos relies on consistent hashing to distribute the load across multiple storage hosts. And as we already saw in previous session, the main advantage of consistent hashing is that the departure or arrival of a node only affects its immediate neighbors, and other nodes remain unaffected. So even though this consistent hashing algorithm presents some challenges, one of those is that the random position assignment of each node on the ring leads to a non-uniform data and load distribution. So for tackling this issue, Dynamo uses a variant of the consistent hashing, which is the virtual nodes. A virtual node looks like a single node in the system, but in the end, each node can be responsible for more than one virtual nodes. So these nodes, from now on, we will call them tokens in the ring. So the main advantages by using virtual nodes is that if a node becomes unavailable, the load handled by the node is evenly dispersed across the remaining available nodes. And when a node becomes available again, or a new node has been added to the system, the newly available node accepts a roughly equivalent amount of load from each of the other available nodes. So the load is distributed evenly. And the number of virtual nodes that a node is responsible can be decided based on its capacity, which is accounting for heterogeneity. So to achieve high availability and durability, Dynamo replicates its data on multiple hosts. And the number of hosts that are replicating the system, we are going to call this setting as N. And each key, as we can see in this figure, is assigned to a coordinator node. The coordinator in the end is the one that performs the replication of the data that falls within its range. So in this figure, node B replicates the key at nodes C and D, in addition to storing locally. That's the way the virtual nodes are working. So just to finish with this partition and replication scheme, the list of nodes that is responsible for storing a particular key is called the preference list. So this preference list is constructed by skipping positions in the ring to ensure that the list contains only distinct physical nodes. Can go to, yeah.
Okay, so what we are looking here is an example of different events getting managed by the application. So in the first arrow, there is everything working normal. There's a second event happening in here, as we saw in previous classes with the process. So this is a single thread. And until here, everything is normal. Once we reach this point, something happens, maybe a network issue or some partition for another situation. But the system should keep receiving all the client requests. So in here, we will keep using this number 2 in both in D3 and for D4. But after that, we will create a new branch for SY and SZ. So once the system get a chance to read all this information, it will be created in D5, which contains information from all the different events that were branched up from any outage on the application. So this is how we notice that here is the SX number 3, because that follows the number 2. And for each D that we are creating in the system, there is a vector clock getting assigned for every event. So now we are going to see a small example of the Amazon shopping cart and how it managed to get synchronization between the web application and the mobile application. So imagine we have this ring with 4 nodes. It doesn't matter if those are physical or virtual. So in this case, we have S equals 4 because that's the total of nodes that we are looking here. And we are receiving N equals 3 because that's the number of nodes that are handling the information. In this case, we are trying to write into D. So D contains this information and it is replicating into A and B. And this is how it looks because of our previous action in the system. But after that, there is some petition to read the information from W, and it is looking on the C. Because C doesn't contain this information, it will go to the closest node, which in this case, it is B. And from there, it should be able to retrieve the information that R is looking. And we will continue with more example of this scenario on the further slides. Okay, so in here, as we saw, it was for the shopping cart and all the different information for the system. And that's like the quorum. And we will see how that behaves on case of any failure or on the high demand seasons. And also we will notice how the replicas perform after any node disappears from the system and re-enters the system. Because as you know, here we do not have any like a master controlling all the nodes.
Okay. How is this quorum approach used by Dynamo? In the end, the main goal is to be available, even if there are server failures and network partitions. So Dynamo implemented so-called sloppy quorum, which is all read and write operations will be performed on the first n healthy nodes from the preference list. So these nodes, let's say, need to be available and responsive from the preference list in order to implement this quorum technique. And which is another way to handle the failures. Consider the example that we just saw in previous slides, the one from the consistent hashing ring. Let's imagine that we have the n equals to 3, let's say 3 replicas. In this example, if node A is temporarily down, or let's say or is unreachable during a write operation, then a replica that will normally have lived in A will now be sent to another node. Let's consider D. So the replica sent to D will have a hint in its metadata, let's say in the call function, that suggests which node was the intended recipient of the replica. So upon detecting that A has recovered, D will attempt to deliver the replica to A. So once this transfer succeeds, D may delete the object from its local store, without decreasing the total number of replicas. So using this hinted handoff technique, Dynamo ensures that the read and write operations are not failing, even if there are temporary node or failures. So in a sense, the preference list of a key is constructed, replicating a lot of nodes across multiple data centers, which allows to handle entire data center failures without a data outage. So we can go to next slide, please. And how Dynamo handle permanent failures using an anti-entropy. What is an anti-entropy protocol? Is a synchronization protocol to keep the replicas synchronized. So To do this, Dynamo uses Merkle trees. These Merkle trees were patented by Ralph Merkle in 1979. They are used mainly for cryptography, but in the end, a Merkle tree is a hash tree where leaves are hashes of the values of individual keys. So parent nodes higher in the tree, they have hashes for their respective children. So in the end, the advantage of using Merkle tree is that each branch of the tree can be checked independently without requiring nodes to download the entire tree of the entire dataset. So how it is done? Basically, if the hash values of the root of two trees, let's say a basic example, if you have two trees, and if the roots are equal, this means that the values of the leaf nodes in the trees are equal, so the nodes require no synchronization. Otherwise, the values of some replicas could be different, which in such cases the nodes may exchange the hash values of children, and the process continues until reaching the leaves of the trees, which will have keys which are out of synchronization. Using these Merkle trees, Dynamo minimizes the amount of data that needs to be transferred for synchronization. Okay.
Okay, so we're back to the example that shows this. And in this case, it is an event W, which tries to write on D. But in this case, once D tries to replicate to A, B, and C, it noticed that B and C are down for external reasons. So Dynamo backend logic allows to D to convert itself in a storage node for the information that it is receiving for W. And once it detects in the system or in the environment any available node, it would replicate to that once it gets available, or if any one of these recovers from the failure. But that's kind of the flexibility that Dynamo presents, that the nodes can change at any time the role that they are having in the environment. So the membership and failure detection is something we already saw. So sometimes when there is a failure, Dynamo doesn't take care of checking why that happened or if the node will come back soon, because that will translate as performance and latency issues for the response to get in time. Remember, the Amazon standard is almost 100 to make the application use smooth. So once the nodes are failing, it just will ignore. And once they rejoin into the environment, it will start assigning random tokens until those get with the load balance that this node is trying to cover. And it will be based on the capabilities of the node that it is getting online. So we also have here the implementation of Dynamo. This will be a little diagram of the request coordination, which means on how the nodes are behaving inside the system, knowing when a node is available for more tokens, when one node is having some struggle to find information, or with the load balance to handle by itself. The local persistent engine, we will talk about this in later slides, but it is also about how to perform some get and put actions from the server or the client side, and from the membership and failure detection, which is something that we already mentioned. But every certain time and by random, the algorithm will ping different nodes in the system and will try to detect which one are deaf and which ones are available again to receive some new task.
Okay. Which are the main parent configurations? We have three main uses, let's say, in Dynamo. The first one is the business logic specific reconciliation. In this case, we have the most popular use case, which is the shopping cart, in which its business logic reconciles objects. Let's say the different versions of a customer shopping cart is merged to have one that is most updated. The second one is the timestamp-based reconciliation, in which Dynamo performs a simple timestamp-based reconciliation logic of, let's say, the last write wins. So the service that maintains, for example, the customer session information is a good example of this. And the third one is the high-performance read engine. In the end, there are services that need a high request rate. So in this case, we have a product catalog or promotional items that will have, in the end, most of them will be read operations. So we can go to next slide. So the main advantage of Dynamo is that we can configure the main settings, which are N, R, and W. In this case, the values of N are used for the durability of each object, and the values of W and R are impacting the other let's say, characteristics like availability, durability, and consistency. So a common configuration used by several instances of Dynamo from the paper is 322, which stands 3 for the number of replicas, 2 for reading, and 2 for writing. So these values are chosen in order to meet the availability service level agreement. We can go to the next slide, please.
Okay, so as we can see here, this is based on around 30 days from customers using the application. And at most of the time, we can see how the write and the reads are pretty low. This is on normal basics. But there are some times that it will increase to almost 100. Because of this, and to reduce the amount to respond to customer again, what they are doing is that for writing activities, as you can see, are the ones that take more time to get performed. So instead of doing that on the real physical hard disk, what they're trying to do here is store this information in the buffer. In that way, they will keep increasing buffer size until the system finds a suitable time to accommodate all this information that got from customer or from the season that cover all these high demand tasks. And once the system gets some free time to achieve those tasks, it will move from the buffer to the physical hard disk, and we'll start working with the vector clocks to sort all this information. And also that's what we can see here. This is for a rare scenario based on the nodes that are present on the system. Most of the times that as we saw, the nodes will easily find the key they're looking for with any of the closest nodes that are to them. But in the worst scenario where they need to keep looking for the less used key or in a far node, this is how it will behave. It will increase the time that it will require to find the key that some request is looking for. But because of the same algorithm behind the scenes, what is happening is that at the given time that the node keeps requesting more keys, it will become closer to more nodes. And because of those physical and virtual nodes, it will be obtaining more and more keys closer to it. So after this period, it will keep balance again. The worst case scenario, it will be that for the old request, always receiving the the farthest key from this node. But that's something that in the practical scenario shouldn't happen.
Okay, what are the partitioning strategies that Dynamo use based on load distribution? We have 3 strategies. The first one was the initial strategy deployed when Dynamo started to be used, and is the T-random keys, T-random tokens per node and partitioned by token value, like the first case. This is, let's say, the same example we saw in the consistent hashing. And this strategy presents some problems because the tokens are chosen randomly, so the ranges vary in size. So as nodes join and leave the system, the token set changes. So the ranges also change, which present some challenges, like the Merkle trees need to be recalculated. As new node joins the system, they need to steal the key ranges from other nodes, and so on. So the 2 other strategies were evaluated in order to tackle these challenges. The strategy 2 is T-random tokens per node and an equal size partitions. So the advantages of this strategy is that there is a decouple of partitioning and placement of the data. And this enables the possibility of changing the placement scheme at runtime. Even though there was a third strategy in which each node is assigned to a Q divided by S tokens, where S is the total number of nodes in the system. So the efficiency in the end depends on the number of partitions. Let's say for strategy 3, for strategy 1 depends on the number of tokens. So there is no fair way to compare these strategies, even if we use the load distribution, while other strategies use the same amount of space to maintain the information. So we can go to the next slide. So we can see the load balancing. We are seeing that in this figure, the strategy 3 achieves the best load balancing, and strategy 2 has the worst. In this case, strategy 3 compared to strategy 1 achieves better efficiency and reduces the size of membership information because the Merkle trees doesn't need to be calculated each time. And even though there is a disadvantage of using this strategy, which is that coordination is required in order to preserve the properties. So we can go to the next slide.
Okay, so for these divergent versions, we have the 2 scenarios, which is when the system is failing for any reason, or because it's facing a high demand of request. In these cases, the system will start creating new branches for all the events, as we saw on the previous slides. And at some time, that will create new versions of the sessions and of the objects that it is handling. And because of that, that will create some, how to say it? These different branches will increase the number of vector clocks that will need to be rearranged or sorted later by the system. And if the system keeps behaving like this in future, it will create so many events that it will take a lot of time or effort for the system to coordinate and rearrange in order to keep presenting and keep maintaining available the application. And because of that, is that we have this client or server driven coordination, which means that some part of these get and put operations happens on the side of the server, and some of them happen on cache on the client server, on the client side. And as you can see on the server driven, it is always a higher number. And this is because they're taking care of the more events like failures in the network or any nodes rejoining and resorting in the environment. But for the client, it is easier to handle and having their local vector clocks, and later passing this to the system for it to rearrange.
So as we already know from all the previous sessions we already have in this class, we know that there are some different background tasks which are used, let's say, for replica synchronization or data handoff. In the end, these are additional to the normal foreground operations. Like in this case for Dynamo, it's the put and get operations. So there should be a way to ensure that background tasks are running only when the regular critical operations are not affected. So in this case, we are using the admission control mechanism, in which we used, in the end, we are reserving some slice of time for the background tasks. And in the end, using this feedback mechanism or this feedback loop, we limit the intrusiveness of the background activities in order to have the foreground tasks, which are put and get operations running as expected. Go to next slide.
Okay, and here we have a short example of what we have mentioned. So imagine having a ring with with these 4 data trying to get inserted. If we are dealing with n equals 3, it will be this operation with the mod. And in this case, the result would be 1, 0, 2, and 2. But if we are trying to escalate to have a new one, a new node, it will be n equals 4. And as you can see, we will need to sort again all this information, because for the first key, Bob, when we have the n equals 3, we have a 1 as a value. But because we escalate by 1 only, it moved to 2. And as you can see, none of these values remain the same. So that will be a performance issue, a network issue, and will impact in the response time for customers. So what Dynamo is doing here is that instead of giving an n equals 3 or n equals 4, it will assume they will keep escalating in the future, and they will give a very big random number named L. And after that, it will keep just adding the nodes as they keep adding to the system or this ring. So even if it is physical or virtual, it will receive a number. And in this way, it will be more difficult for the nodes to having to rearrange all their information or the values, as well as the neighbors that they are pointing to. So before we finish, this is how the system will be pinging different nodes to verify if they still alive. If after a certain amount of epochs or pings that the system gives to given nodes, if the ping cannot be found as alive, it will be declared dead and will start sorting again. And as you can see, after the customer kept adding information to the tables, there are these nodes A, B, C, D, and well, this was E. But the thing here is that A belongs to both snapshots, and this will need to be sorted with the vector clocks, just to notice how complex this algorithm can be. And that's some of the reasons of why Amazon doesn't share the code or the actual implementation of this, because that still means a competitive advantage for them, the way they are sorting all these writes that happens during one day, but they, after some time, will find a way to accommodate all these values in the given order.
So we can conclude that the Dynamo, by using all these decentralized techniques, they can be combined to provide a single highly available system. So its success in one of the most challenging application environments, like the the Amazon e-commerce system or page. This shows that an eventual consistent storage can be a building block. So one key insight of Dynamo is that their storage system can be configured to have their desired performance by tuning the parameters and R and W. And finally, Dynamo, as we said, can be a scale out, as from the beginning of the class, Madi mentioned that scaling out stands for horizontal scaling. So this is based on their current request load. So this could be considered one of the main techniques used by Dynamo in order to advance the state of the art. And that's it from our side. Any questions?
I have a question. What would be a disadvantage of this algorithm? I mean, it sounds like nearly perfect.
Yeah. One disadvantage is that in the end, if as you remember from the techniques for partitioning, the main disadvantage in this case is that changing the node membership, let's say if new nodes are being added to the system or nodes are leaving, there is coordination or this requires coordination in order to preserve, let's say, the properties that we have mentioned, the Merkle trees and the tokens, let's say the virtual node ranges in which the keys are being spread over the system. That could be one disadvantage.
Yeah,
But I think that disadvantage is already fixed, right? Because you say that they are using a big L number, so you don't need to worry about adding a new node or leaving a new or a node leaving the circle.
yeah, that will also impact the consistency, because if you're looking for consistency, this is not the algorithm to use. And also for the another disadvantage, before answering fully your question, it will be the size of the data that you can use. Remember, for the put and get operations, we are dealing with 1 to 5 megabytes of memory, or the size for the information to handle. And yeah, regarding the big random L, it is just to avoid having to rearrange all the nodes, but that doesn't exactly mean that at some point you will reach that moment and keep creating the virtuals with all the tables and the information that will create a lot of vector clocks that you will need to rearrange in future.
Okay, thanks.
Other questions?
Any other questions?
I have one. During the performance graphics, there were some demonstrations of how the buffering is working whenever there is no time for write in that precise moment. So how does the buffering actually works? I mean, in some point there should be no, wait for write, right? In some point, if there is too much buffer now, you need to write because you need to do it, right? Or how do they solve that?
As far as I remember, the paper is not that specific in the techniques that they handle on the backend for all that information, but we're just assuming a lot of things, that for this buffer, it will keep increasing until at some point the system will find a suitable time to start writing. But as we mentioned, there are some competitive advantage from Amazon, and they are not giving like all the numbers and all the code on how they're performing this. So not sure if you Hector, remember something else.
Yeah, as you remember, Dynamo is an eventual consistent. In the end, the system is configured so that we have at least one replica in order to perform this write. Yeah, we can say that the scheme used by Dynamo trades durability for performance. Let's say a server crash can result in missing writes that were queued in this buffer. But in the end, this is something that Dynamo allows to configure so that at least we can have one replica to perform this write, which is tuning the W parameter as 1. I hope this answers your question somehow.
Yep. Wins.
I have another question. You mentioned, Chris, and I think that as a main advantage, the application for clients can tune the values for N, then I think that is for node, R and W, to achieve their desired levels of performance and availability and availability. But which of them determine the durability of the object? N, W, or
N.
R?
And which are the nodes in which we will have replicas, the nodes that will be replicated.
Okay, in this case, W and R determine the availability in this case?
Mm-hmm. Availability and also consistency.
Okay, thanks.
One little question here. I don't know if Amazon provides that information, but when you say that a write operation is performed, you said in one of your graphics that, for example, the node C decides on which other servers replicate the data. It is provided an algorithm to decide in which servers the data will be replicated, or it's supposed?
Yes, actually, there is nothing provided because in one slide it is mentioned that this can be done in either by the application or the service itself, the Dynamo. Most of the times, I guess, this is done by the application, or I can imagine that Amazon tried to keep this information by for themselves because we investigated in a lot of places, but anything was shared in terms of implementation.
Okay, yeah, thank you.
Any other questions? I send you a link in the chat. Can you please answer? Thank you, guys. It was very, very detailed, really, really nicely presented everything. So maybe we just finish the class because you covered everything, really. It was great. But let me share with you. Stop sharing. Share. Yeah, it's my cat. So now I have two. That's why it's like it's a little jungle here. Okay, thank you guys. Maybe we can have like a 10 minutes break. Then we come back and I briefly talk about certain things, but really there are not much I can add. Just some other stuff I can just explain a little bit more, like clarify. That's it. So let's come back by 8:25, so we can finish earlier, 5 minutes from that side.
Okay.
Okay. As I said, I believe they did really good job covering almost everything. So I just want to go some of them, maybe explain in a different way, different manner, some of them. So this is where I stopped, right? About the questions. So they already talked about this, about the concept of the context, which is basically it's relating to the version, what version of the data. I didn't talk about consistent hashing, vector clock, eventual consistency, and those are basically the technologies that, not technologies, let's say algorithms that they use, the ideas that they use, as they mentioned. It's not that they come up with amazing things, but they did actually, but not that something new, but merging all these ideas, they could build an amazing like database system, like distributed systems. So as the key trade-off, I mean, like there was a question, like it sounds like a perfect system. It sounds like perfect. I mean, it's good, perfect, maybe near perfect. But of course, as they mentioned, it's more about how to say, they sacrifice in consistency to achieve high, basically response time or high availability. That's why, I mean, you can use it for certain application, not it's necessarily can be used for all the applications. So we talk about this, they talk about the preference list. Let me see, okay. Okay, there is something, they mentioned something like that basically Amazon achieved something like near to zero hop distributed hash tables. If you remember last time we talked, that we talked about some ideas that, okay, you have the hash tables, how you can look up for the keys. We talk about the basic lookup, you look at the successor all the way until you find the system that has basically the value that you're looking for, the key. Or then we said, okay, let's use that finger tables in order to do it like a near binary. So we could jump it like a very much fewer jump. We could basically hop. We could reach to the system that has the data, the key. But they mentioned Amazon is almost in the zero hop distributed hash tables. So, and how they achieve that by something like we can call it a gossip and lookup. So what they do is like once per second, each node contact their randomly chosen other nodes. And then they start exchanging their list of known nodes, including virtual node IDs. So assume all nodes will come back eventually, and there is no basically repartition. So eventually, all the nodes get to know about basically other nodes. So that's how they can basically achieve this zero hop distributed hash table. Not necessarily it can be zero hop always, but it can get to that point at some point. I mean, it can get to that level of performance for a lot of operations. That's why they can reduce basically variability in response time using these schemes.
I have a question in that kind of area, which is we've been looking at the load balancing calculations between the nodes trying to distribute evenly the data, but in some point the data hasn't been rated. Like okay, let's say that each uh, 5 pairs of key values are stored in each of the nodes, and that would make the system balanced. But what happens if, for example, in this case of zero hopes, um, it could be like the data which is more busier are on the on the first and on the second node. Is there any kind of technique to achieve this load balancing, rating like the data, or how much that data has been accessed? Like, I don't know, like in some point having some cache. I mean, I just thought at the first, I think the previous class when we were looking at the distribution of the nodes and the data, why there isn't any relation with the binary, search. I think it was mentioned, and also some, application of some certain of cache information, allowing you to like rating the most visited nodes, or the most read or read data, and then kind of applying the load balancing in that specific uh, new information of the system. It's like a live system, and it should be changed in during time. Probably with taking this example of Amazon, I would think that during Christmas, all of the Christmas gifts and articles related to Christmas are the ones that are being looked up like heavily, and then mid-year, I don't think people is looking for those. I mean, just fewer now. So is there any kind of like load balancing, rating the data that is being stored, or it's just okay, each of the nodes should have like 5 pairs of key value?
Actually,
But go ahead, Paul.
okay, yeah, I can answer part of that because, I was working at Amazon, and actually there are some like stories about.
You should be.
I'm sorry?
You should be very sure that you're not violating any kind of
No. No, that
Nice.
it's not. I know that it's not. It's because there are, like, for example, there are some stories where Amazon was actually on Black Friday. They had a hot item like sold, and everybody was trying to purchase that item at the same time, and the database crashed because of that. So actually beforehand, like before these hot days, like for example, Christmas, Black Friday, and things like that, people actually manually create more replicas about the information, about the trends and things like that, and with the speculations. And they purchase a lot of servers only for a while or enable more nodes. And during that time, it's usually like 300% of the capacity. And during that time, the most rated or more popular items are the ones that are more replicated. And then after that date, they go back to less servers. So I don't know if that, usually at runtime, this is not handled by Dynamo. Also something to mention about Dynamo that I don't know if it's like about this topic or not, but it's really highly, how you say, it performs a lot of writes, mainly because the data is not like verified when writing. For example, you perform a write and the data is not checked if it was written correctly. Another type of databases, what they do is they perform a write and they read again the value and they compare the values to see if the data was written correctly in the database. But what Dynamo does usually, it's they perform like several writes to different master partitions, and the probability of all of them failing, actually it's really minimal. But this way they perform like how you say the high speed on the writes, because they are not checking. When they check if the data is consistent, it's only usually on the reads. But those are like the main two things. Like Dynamo usually doesn't check like that high if you are querying the same type of data a lot of times, usually that's done beforehand. And also usually when you are constantly checking the loads, just so you have different thresholds when on the reads and on the writes on the servers. And usually when they reach around, let's say 80% of the, of the capacity, you start creating more nodes. So to distribute all the load. So usually you don't let more, let's say, than 80% of the capacity to be reached. And if it's reached, then you start loading, creating more nodes. Does it make sense? I don't know if that asks your question. Solves your question, I'm sorry.
Actually was more like what sort of mechanisms. I mean, you answered at the first, like they just replicate more, but it sounds like it's a really elegant algorithm, and then when it comes down to just add more items to the hash or the hashes, that sounds kind of sloppy, or not that elegant, but that's okay.
Okay, thank you, Paul, for addressing the questions. I agree with him, and but I don't get why you say. I mean, I don't want to say it's elegant way, but or not. But why you think it's not the best way, Roberto?
Well, I get the thing about, well, integrity is just one thing that they didn't mention in the entire presentation. So that means, like Paul said, it's just writes, and they don't care about the integrity of the data. And the second thing is that they just seems like they just write, and then there should be like a better, I mean, I know that they have a lot of infrastructure, they leaders on that, but it seems like scaling up, there's a better way to use these resources. Like for example, maybe you can cache all the writes and see if you already write those the same write sentence, and then you can just cache that or reuse that, or just point to the same node and say that you already wrote that. But that would mean, or that would end up being on a read to the entire hash set or distributed hash table. So I would think that would violate one of the rules, that it's just they just care for writings and not for reading, or that would add the the extra layer of logic. And then
okay,
but
because again, I mean, the application matters, right? I mean, you're designing what system for what type of applications. I mean, Pedro, you want to say something? Go ahead.
Yeah, but he says that they don't care about the read, but more about the write. But well, that's on brand, right? The slogan is they are always going to write, so they are doing. And again, I think they prefer to have a better experience for the client that didn't involve a lot of performance issues.
Yeah, again, it's like application dependent. What type of system or distributed system you're designing for what type of purpose, right? So as long as I can sell, I can let them add more, like let's say, goods to their shopping cart without interrupting them. Okay, it's fine. In some cases, yeah, there would be conflict, as they were describing. Yeah, I mean, anyway, like the worst case, even if the system, the Dynamo couldn't handle it, the application couldn't handle it at the end, it comes to the user, right? You say like, oh, there is like, maybe there is deleted items in your shopping cart that now you see it again, so you just remove it. So I don't want to say it's like the best way, but it's working the best. I mean, at least, I mean.
Also, some things that I think that are important to mention about Dynamo is, like, for example, you can, when you are writing registers, you can add fields or remove fields, no matter what. Like when you are making a query, you can add, like, for example, if you have a car item, a car registry, and you want to add a new property, you can add it like super easily. And also, usually you use DynamoDB when you know which type of queries you want to make, because you have something called how you say index and secondary indices that usually you use these indices to design which type of queries you want to make beforehand. So usually Dynamo, it's like a hybrid between it uses in the background MySQL that to create the type of queries and to know exactly where the data is stored, and it saves the data in files, in chunk of files. So these tables that it's only the metadata, it's created because of the type of queries that, well, of the indices and secondary indices. So that's why also Dynamo it's like really fast, because it's already planned with type of queries you are going to do. So it's not like you can you use it like for any type of purpose.
Okay, thank you. I mean, sorry. I mean, Paul working for like devil companies, so he's defending it. So it's I'm joking. Okay, yeah, but let's continue. But I think I mean the Paul addressed the questions. Yeah, yeah. So yeah, as I mentioned about this already, like partition forces a choice between availability and consistency, because you cannot, I mean, the partition is there, so you have to deal with it, and then you can sacrifice the basically availability or like consistency, like partitioning in there, so you're sacrificing consistency for sake of availability. What I wanted to say here. Yeah, it's the same thing. I mean, talking about the cap theorem. So they already talk about the quorum, like a sloppy quorum that Dynamo is using. So what happens is like I mean, you sacrifice consistency to allow progress. And Dynamo tries to store all the values put under a key on the first n live nodes, the same thing that they were talking about, this n value of the coordinated, the preference list that also they mentioned. But to speed up the things, right, they mentioned also already coordinators return sixes for put or write operation when the number of like W is smaller than n. They mentioned the default setup for the paper, I mean, not setup for the paper, but the recommended value, the thing that paper is discussing, like either like tree replica, you wanna, this read and basically read and write operation, or that 2 and 2 is, that means you wanna be able to write in 2 replica, and you wanna be able to read from the 2 replica because before confirming the operations. That's the whole idea. When you have 3 replica, you wanna be able to write in 2 and read from 2 in order to, let's say, consider that as a success. So that's I mean, that's those values are referring to that actually. They also talked about in the handoff. Okay, so suppose this situation that you said n is 3, you want to be able to write on 2 replicas. Okay, but let's say you doesn't receive replies. Okay, from W, but from 2 in that case, to do a put operations. So you could, in this case, you could return failure. But remember, the idea of the Dynamo is like high availability for writes, right? So even if this happens, okay, you can have hinted handoff. What is that they described us? So let me describe it a little bit more. So the coordinator tries further nodes, not those 2 nodes from the preference list. He tries other nodes that are not in the preference list, okay, to do the put operation if it's necessary. So it indicates the intended replica nodes to recipients. Basically, as they mentioned in this figure, so you're supposed to basically do the write operation here. You cannot because it's failed. So you do it in, let's say, the next one, okay, or in other nodes. beyond those two nodes in the preference list. You do it in E, but you inform E that you're supposed to write this information on the C. But the C is failed, so you're passing that, basically doing the put operation in E. So you basically, as they mentioned, you hint E that the original recipient of this information is node C. So what happens, basically C keep pinging, let's say, this node C, to see when the C come back alive, okay, return to the system, so you can forward the replicated data back to the C, back to the original data, back to the original location where it's supposed to be. So that's the idea with the hinted handle. So that the recipients, which is now the new recipients, which was not original one, it's not supposed to be the one, will periodically try to forward the intended replica to the original node. So something it's interesting in the paper in like last paragraphs in subsections 4.6 in the paper. If you, I mean, in other things, I mean, you're supposed to all read the papers, right? Not that just the presenting paper, presenting groups, but it's fine. So it's mentioned that the preference list always contain nodes from more than one data center. So it's not just like your preference list is just from nodes in one data center. So there is always more nodes in your preference list that they are in different data centers, okay? So you can make sure it survives all sorts of failures. Even if the tornado came, wiped out your data center, the data still survives, okay? So that's something I wanted to mention. So again, the same thing for the read operations, okay, for the get operations. Suppose coordinator doesn't receive R replies when processing a get. In that example 322, R2, you want to get reply from 2 replica in order to basically consider that operation a success. So R is the minimum number of the nodes, like 2 in this example that we're talking about, that must participate in successful read operations. But if it doesn't receive this 2 number, if you get replies from 1, you can consider that a fail. But the idea is like, why not return whatever data you can find, okay? Because at the end, there isn't, I mean, the consistency is not guaranteed. So you can think about that that scenario as well. Let's see, nothing here. So they talked about the conflict resolutions, okay? So it's, as I mentioned, in some case, the Dynamo tries to basically do that automatic resolution of the conflict using that vector clocks or version, version vectors, or it's the same, almost the same concept with vector clocks. So as I mentioned, sometimes the Dynamo itself cannot resolve the situation, so it passes the conflict goes to the application level in order to do something about that particular conflict. They talk about version vector, or same, more or less same idea with vector clocks. So they mentioned this, so I skip. Same thing. And there is this talking about trimming version vectors, because that version vectors that you are having, you can get long, okay, but it's not supposed to grow forever, the version vectors that you have. So in practice, basically you truncate basically that list, the version vector list. So let's say, for example, when version vector is bigger than 10 nodes long, version vectors drops the timestamps of the nodes that least recently processed. So let's say you just keep the last 10 operations, okay? So when you start truncating the list, you don't want to keep that version vector forever. Um, so let me. So we talked about that, the hinted handoff, right? That when the node crashes, before it can replicate data to the node in the preference list, right? Then we talked, you can go beyond that preference list and do the copy in another one. And about the replica synchronization, and at the end, you wanna have the data, basically the same data in different replicas. When they come back to the, basically they come back to the system, to the operations. And how they do that? They use Merkle trees. They talk about what's Merkle trees. It's like basically a trees, like hash value trees. Merkle trees is hierarchically summarize the key value pairs of a node holds. Basically, in Merkle tree, we have a leaf nodes. We are talking about trees. So we have a root, we have a leaf nodes, then we have different branches. And the whole idea here, you want to detect the mismatch in your data, right? And the whole idea here is how you can do that the most efficient way to find the mismatching between replicated data. So imagine this is basically two Merkle tree. You want to compare them and find where is the data missing. That if you notice it's missing, there is one missing here, okay, and one missing here. So you want to be able to detect them. So how Merkle tree works, basically you have the hash value of the data stored here for all the leaf nodes, hash value. Then here you have the hash value of these two combined. And here the same, then here you have the hash value of these two hash value, okay? So when you want to find the mismatch information, you start basically from the root. You look for, basically you compare this hash value here with this hash value here. If they don't match, it means there is some data change at some point in the tree, right? But that value start propagating to the root. These two values are not different. Then you come in a lower, basically lower level. Then you compare the hash value again for these two, Then you find, for example, that it doesn't match. Then you compare these two hash value, like this one, say this one, and this one with this one, right? Then you see these two hash value are the same. So it means there is no change here in this branch. And these two like hash value is different. They are different. So you know this is the part that basically something happened or some information are mismatched there. So basically it's a very efficient way to do lookup for changes in the file. I believe GitHub using this, okay, and in a very interesting way. Of course, Amazon Dynamo using the Merkle trees, and it's, as they mentioned, it's more used for how to say cryptography, but it can be used in distributed systems like GitHub, as I mentioned, or for DynamoDB. So yeah, the idea is like finding difference key quickly and with the minimum information exchange. So there was a question from Dorle about this, the number of replica, let's say read and write that you want to have. This is the value mentioned in the papers. So you want to have 3, you want to be able to read from 2, write from 2. And it gives you a good durability, good read-write latency. But if you set, because there are like a tunable parameters, if you set you want to write on 3 and you want to be able to, sorry, you have 3, you want to be able to read from all 3 to consider your get success. And you want to be able to write from 1. So it gives you a slow reads because you want to make sure you're reading from all this basically replicas, and it gives you big durability and fast write because you're just writing in one replica. So if you consider read 1, write 3, it gives you slow writes, strong durability, and fast read because read is 1. If you want to read from all your write to all your replicas and read from them, then it's more likely that read sees all prior writes. And if it's considered 1-1, then read column doesn't overlap write column. What does it mean here? They don't overlap if you have 3, okay? And remember, oh, sorry. The idea is if you, this is the situation, right? 2, 2. So if you do this 2 for write, any other 2 that you choose with this one, you're going to have one overlapping basically column. But if you don't consider that, if for another 3 you consider just read from 3, read from 1 and write from 1, you may be, the situation can something like this. You write here and you read from this. Okay, so there is no overlap between there. So it doesn't basically can work, let's say. So anyway, there are tunable parameters. Depend how you tune them, you get different type of performance. And that's why you can do that actually, tune them. So the takeaway idea from this Dynamo is consistent hashing broadly useful for replication, not only in peer-to-peer systems. Dynamo has extreme emphasis on availability and low latency, usually at the cost of some inconsistency, but not a big deal for a system like Amazon. And eventual consistency lets write and read return quickly, even when when we have partition failures. So we already talked about eventual consistency. So basically, we covered that too. So even by considering that, you can do that read and write operation quickly. And version vectors allow some conflict to be resolved automatically, others left with the application, as we talked about. So those are basically takeaway ideas. We are done with the class. Is there any questions? All good? Okay, perfect. Thank you guys for being here for the 8th week. Okay. See you next week. Another thing is like you can start booking the time to have a. The idea is with that one-to-one talk. Let me again clarify what does it mean. Is like the whole idea is for me to get some personal feedback from you about the course, about if you are struggling with some special part of the course, okay? Or if you have a problem you want to talk about, okay, I want to talk about this particular topic. Okay, so there is no special format. It's like more casual talk. Okay, take care guys. See you next week.